Thank you very much for the introduction and for the invitation. Somehow this whole topic of the workshop brings me back to the early years of 2000 when at Duke University we had this project we called biogeometry, and that's how I met Patrice, and Michael Levitt was part of it. There was a bigger group, and we did mathematics, computing, structural molecular biology, and I learned a lot about biology. But I also noticed that new things are necessary in mathematics, and somehow this brought me back into topology. So after learning geometry and biochemistry, I went back to topology, and there was another string of activity. The first three topics here. The second topic was the RAP algorithm, which was more targeted towards industrial applications, shape description. Anyway, so after these excursions into biology, industry, and topology, I think it's time to bring the three strands together, because it's really aspects of one theory, and I think bringing the theory together gives new facilities. And then somehow today what I'd like to do is explain this partially on a historical background, and also indicate of how it fits together and what could be possible which has not been possible before. So these are the first three topics: biogeometry, back to Duke at this project, RAP, the industrial application, persistence, the excursion into topology. And recently we also looked at what happens to these structures in a random case, Poisson point process, and I'll talk about some results there. Really, by looking at the topological structure or some features there, we found new results on alpha shapes in a random case. We do not have results on RAP complexes in a random case or persistent homology in a random case. These are still open questions, but I want to say a little bit about how much we know or how little. So this is the plan. So I start at the beginning, that I learned from biochemists that you can actually, to some extent, think of a protein as a geometric object. So the standard idea there is to replace every atom by a sphere, possibly different radii. Here they're all same radii. This is hemoglobin, colored conveniently, so you see the four different domains that come together. So this is responsible for us to be able to breathe. And as a geometer, I would first want to decompose this thing. So I think of it as a union of balls in 3 dimensions. I call them balls instead of spheres because somehow there's this subtle difference between the sphere being the surface, the ball being the volume, and I try to stick to that, although the terms are used differently in different areas. So anyway, so there's a union of balls, and I would like to decompose it with a Voronoi diagram of the points. So this you get when you take every center of a sphere, that's a point, and then for each center you assign the convex polyhedron of points where this center is the nearest. So you cut this into convex pieces, then you take the Nerf. The Nerf means that you take all the points as vertices. If 2 Voronoi domains restricted to this union intersect along a 2-dimensional thing, then you draw an edge. If 3 intersect, you draw a triangle, and if 4 intersect, you draw a tetrahedron. I'll illustrate this in 2 dimensions. And we call this Nerf the alpha complex, partially because of historical reasons. So when the alpha shapes or alpha complexes were introduced, alpha used to be the radius. But somehow there was this migration of meaning that nobody uses alpha as radius anymore, but sort of as a name. So it became a name for the shape or for the complex. Okay, so I'll do this slowly in 2 dimensions. Here are my centers or points. Here is my union of balls or disks. Here is my decomposition into Voronoi domains. So each disk is cut by or clipped back to the Voronoi polygon. Everything is convex because a Voronoi polygon is intersection of half spaces or half planes in this case. And so I can take the Nerf and call this, now I call it the Delaunay complex. So somehow because of notational reasons, alpha complex, now we call it sometimes Delaunay complex in order not to make a difference with Delaunay triangulations. The reason for that is every alpha complex is a subcomplex of the Delaunay triangulation. And it's sometimes a nuisance to have two different names, so I call it the Delaunay complex for a radius. So the notation here, Delaunay complex for radius r, x is a set of points. Okay, so by the Nerf, maybe I indicate again, I have an edge if two domains meet along a line segment. If three meet, let's see, here are three, here I have a triangle because 1, 2, 3, they meet at the common point. If I increase the radius, you see the union of disks grows. I can extend my Voronoi domain, and then I add a few simplices to the Delaunay complex. And here I want to point out somehow that most of the added triangles, so they are darker here, most of them are anti-collapses, which means a triangle comes together with an edge. It's really just thickens the shape. The connectivity otherwise does not change. Let's see. Here I have two such anti-collapses, one. The only exception is this edge up there that comes by itself. And this difference is going to be significant. So if you grow a little bit, there's two cases that happen. There's simplices are added by anti-collapses. Anti-collapses do not change the homotopy type, which means the global connectivity. And sometimes a simplex comes by itself, like an edge. When an edge gets created, in this case, it forms a loop. So here I have a little hole in my union of disks, and I have a hole in the alpha complex. Sometimes when an edge gets in, it merges two components. But we'll see about this later. Okay, so this was the notion of alpha complexes, and then for some time we were busy to try to figure out what this is all useful for. One is it's a convenient way of measuring proteins or unions of balls. So there's an inclusion-exclusion formula which says that the volume of the protein, so this union of balls, is an alternating sum. And the alternating sum goes over all simplices. So the Q is the simplices in the Delaunay complex, where I take the sign alternative with the dimension and the volume of the intersection of the balls in this simplex. We're in 3 dimensions. So I have simplices of dimension 0, 1, 2, and 3. For 0, I get a ball. For 2, I get the intersection of 2 balls. For 3, I get the intersection 3. And for 4, I get the intersection of 4. So if I'm able to compute the volumes of these things, then alternate in the sum, I get the volume of the whole union. There are similar formulas prior to this. Kratky, I think, was the first one, an Austrian chemist or physicist. I'm not sure. I somehow never managed to meet him. And Kratky, unfortunately, is a common name in Austria. So I even contacted people called Kratky at the universities, but they always pointed me somewhere else. And he had, in the 70s, he had something like the existence of similar formulas, not quite as short and not as concrete, but similar type, in 2 and in 3 dimensions. This is in n dimensions, if you like. And it gives a good way to compute the volume of the union, but it extends. You can also compute the volume of voids. There are even shorter formulas for that. pockets. You can compute the area with more or less the same formula. With Patrice, we worked on computing the area derivative when all the atoms move for molecular dynamics. The volume derivative, we had the weighted volume derivative. Okay, so this is kind of the excursion into combinatorics. Inclusion, exclusion works beautifully with alpha complexes. There's a classic theorem which is called the Nerf theorem, which is relevant in this context. It says that the alpha complex is connected in the same way as the union of balls. So if like in the hemoglobin you saw in the middle, there was a tunnel through, the alpha complex of this also has a tunnel through it. The technical term for this is the homotopy equivalent. And the Nerf theorem goes back to Leray, or sometimes to Barsouk, 1948. It says if you have geometric sets such that the intersection of any subset is either empty or contractible, then the union of the sets has the same homotopy type as the Nerf. And we're in this situation because our sets are all convex. Convex, the intersection is again convex or empty. Therefore, we have homotopy equivalence. Okay, so I just wanted to state this. And homotopy equivalence is a little stronger than having isomorphic homology groups, and I'll get to this later. Okay, so instead of just claiming that it's the same homotopy type, for this union of balls, you can actually create a deformation retraction, which means I deform the union so that at the end I get the complex. And this deformation is continuous, so that's a proof of the homotopy equivalence, a very constructive proof, which in this case is possible. So we did this video, I don't know, a long time ago. And you see each sphere shrinks. When two spheres meet in a circle, the circle gets extended into a cylinder. Then the circles where the spheres intersect, they meet at corners usually. The corner expands into a triangle. And otherwise nothing happens. So the vertices become triangles, edges become cylinders, spheres shrink. And then as this continues, I get my alpha complex. Okay, and I just need to realize this is continuous, so this is a proof of homotopy equivalence. But the Nerf theorem is much more general than this. Okay, there's lots of things I could say, but I'll come back to this anyway. I should also mention, I forgot at the very beginning, so you don't have, so you have the right expectations. This is a mathematics talk or computational talk. Unlike Patrice, I did not change field and I did not become a biologist. But I hope that all this stuff is going to be more useful for structural molecular biology in particular. Anyway, so now I come to my second topic. The second topic is the RAP algorithm. So this goes back to 1996, I believe. And it grew out of alpha shapes, but there's an important new ingredient in there. Namely, in a nutshell, the ingredient says something like, there's a glue between the simplices that allows you to talk about larger chunks of the triangulation. So instead of taking simplex by simplex like we do in alpha shapes, I take chunks of them together and they have a meaning. And this gluing together is produced by a discrete flow. So let me first start with the notion of collapses. So you remember in 2 dimensions we had this anti-collapses where I added a triangle and an edge. I call it an anti-collapse because a collapse usually takes something away. Anti-collapse adds something. Okay, so when you do a collapse in a complex, there's various types. So let's see, we have here at the top, this means that I have an edge with 2 vertices. One vertex is not connected to anything else, so I could just remove this vertex and the edge and leave the remainder. I call this a 0-1 collapse because a 0-dimensional simplex and a 1-dimensional simplex disappear. And you can imagine sucking this vertex into the other vertex. So you see this deformation retraction happening. And in fact, every collapse can be, you can create a deformation retraction that proves homotopy equivalence. So collapses do not change homotopy type. Let's see, the second one is a 1-2. So it means an edge disappears and a triangle disappears. So what's remaining is the two edges. So this is like pushing the triangle in. And here we have another collapse, a tetrahedron. And what I remove a triangle, the front face, and the tetrahedron. So it's always a pair of simplices, and the dimensions of these two simplices that I remove are adjacent. 0, 1, 1, 2, 2, 3. But I can also combine it, such as in a 0, 1, for example, I could follow up with a 0, in a 1, 2. I follow up with a 0, 1. I could remove another edge. So then I call this a 0, 2 collapse. A vertex, two edges, and a triangle disappear. And just pushing it flat. And in a tetrahedron case, again, I have, instead of just a 2, 3, I also have a 1, 3. Edge, two triangles, tetrahedron disappear, or 0, 3, where I make the whole tetrahedron flat to a triangle. And these operations will be instrumental in creating this glue that allows us to look at simplices in bigger chunks. But what's useful for that is to draw it more abstractly. So I would like to introduce the notion of an interval. So an interval is a small set of simplices, namely exactly the simplices that are removed in a collapse. Let's see, here's my, explain the drawing. So each node is a simplex. I draw the nodes bottom up, where the dimension increases when I go up. So at the bottom, usually I have vertices, and then I have edges, and I have triangles, and I have tetrahedra. And if a vertex belongs to an edge, I draw an arc in between. So this would be a vertex and an edge. This would be the picture of the 0, 1 collapse. But it's also the picture of a 1, 2 collapse, when the lower node is an edge and the upper node is a triangle. Or the lower node is a triangle and the upper node is a tetrahedron. Then this is the 2, 3 collapse. So in fact, all the elementary collapses, which is the left diagonal, they all have the same picture. Just two nodes on top of each other. And I call this an interval. The next interval, more complicated one, is if the top node and the bottom node are 2 dimensions apart, then I have two simplices in between, like a vertex, a triangle, and 2 edges. So this is the picture of the second diagonal. And then over there, the last picture, this looks like a cube, is the picture of a 0, 3 collapse. That's when the lower bound and the upper bound are 2 dimensions apart, like a vertex and a tetrahedron, and then I have 3 edges and 3 triangles in between. And this is a general pattern. So if I go to higher dimensions, intervals, when I look at this Hasse diagram of the interval, is always a skeleton of a cube of the appropriate dimension, which tells me that the number of simplices involved is always the power of 2. Okay. So now I would like to introduce a little bit of generalized discrete Morse functions. So discrete Morse theory was introduced by Robin Foreman. 1998 is probably the most important paper that's always cited. And I would like to generalize it a little bit. So I call it a generalized discrete Morse function. But as far as I'm concerned, the generalization is only minor. But this minor modification somehow makes things much more convenient, and it fits perfectly to the alpha shapes and the rest of what I want to talk about. And I would like to just define the generalization. I'm not going to give you the details and some other transformation from the original theory to this theory. I'll just give you the definition that I use. Namely, I have a simplicial complex, and I define a generalized discrete vector field on it. And what this is a partition into intervals. Partition in a mathematical sense, namely that every simplex belongs to exactly one interval, not 2 and not 0. All right. So this is called a discrete vector field. And in order to have a discrete Morse function, I need this discrete vector field to be acyclic. And if it's acyclic, then I can enumerate the intervals in sequence. I can give function values to the intervals in a unique way. Not in a unique way, in an increasing way. And I'd like to show you that actually cycles are possible. So cycles are not bad. It's just when you have a cycle, you don't have a gradient. So it's like the difference between a gradient field, which is acyclic, or a general vector field, which can have cycles. So they are they're interesting in dynamical systems and so on. I will only be interested in gradient fields. So we're acyclic. So here's an example of where cycles can happen. So here I have a simplicial complex, just a triangle with 3 edges and 3 vertices. My intervals are vertex edge pairs as colored, and the triangle is itself an interval. By the way, I forgot to mention, if there's an interval in your partition which has only one element, then the simplex is called a critical simplex. It's perfectly allowed, and a critical simplexes play a special role, so we'll pay attention to them a little bit later. Okay, so I have this particular partition into intervals. Now I draw the Hasse diagram, so I have one triangle, 3 edges, 3 vertices. The arcs always go up, and that the color shows the pairs. So I have 3 pairs or 3 intervals. And now, in order to show the cycle, what we do is we create a directed graph by making all the intervals nodes. So I contract the intervals into nodes, so now I have 4 nodes. And if I have an arc from one interval to another one, meaning one simplex to another simplex in the second interval, then I draw this arc, and now you see the cycle at the bottom. So this example is not acyclic. Okay, so this is not what we're interested in. We're interested in cases where we don't have cycles. Oh yeah, I should mention now. To connect this back to the alpha shapes. So the way I showed you alpha shapes is we started with the alpha complex, and then we thickened everything, and then we get a slightly larger complex. So you should think of this process as a continuous process. All the balls grow slowly, and then a simplex will appear at a certain moment. And then I call this the radius of the simplex. So now I have a function from the simplices in the Delaunay triangulation to the real numbers. This function is, well, it's just well defined. You might ask yourself, what is the radius of a simplex really? It's the radius of the smallest empty circumsphere. So for a triangle, you would try to find a sphere that passes through the 3 vertices. It has to be empty, meaning all the other points have to be outside. Now you have a whole pencil of such spheres, and you take the smallest empty one. The smallest empty one could be the smallest sphere that passes through the 3 vertices. In this case, the triangle is critical. But it could also be not the smallest sphere, but rather there's another point that pushes the sphere on one side, in which case it's not critical. It's going to be part of an interval. But in any case, so this is the definition of a radius or radius function. And then it's not hard to see that this radius function satisfies the properties of a generalized discrete Morse function, meaning that the simplices is in an interval. They have all the same function value. So they appear at the same time, and otherwise the function just increases. And so this shows acyclicity. Because if you are able to assign function values, it must be acyclic because you just increase the function value and then you get the intervals in sequence. So what I'm saying is the radius function of the Delaunay triangulation, which defines the alpha shapes, because every alpha shape is a sub-level set of this radius function, is a generalized discrete Morse function. Okay.
So the vector field you get from that function is?
The vector field I get from this function are the intervals. And the intervals are defined by these spheres that define the radius. I stay in 3 dimensions, because in 3 dimensions it's slightly interesting. For example, if you have an edge, but there's another point here, so that the smallest circle or smallest sphere through this edge is not empty. So my sphere is pushed in this direction, so my sphere looks like this, with this center. So now the radius of this triangle is the same as the radius of this edge. So I get this as a pair, or an interval of size 2. Okay. Maybe I'll show you also the example of an interval of size 4, namely an edge and a tetrahedron. So there, the case would be, let's see, there's a sphere in 3 dimensions. And there's the 4 vertices of a tetrahedron are all in the front sphere. And I'm interested in this edge. So again, the smallest sphere of this edge is not empty, contains these 2 points, so it pushes it back. And then the sphere is equidistant, so it contains all these 4 vertices. And therefore, the function value of the tetrahedron is the same as the function value or the radius of the edge. And these triangles will also have the same function value. So this is, in 3 dimensions, this is a picture of an interval of size 4. Intervals of size 8 don't exist in 3 dimensions. You have to go 1 higher dimension. Okay, so this defines the intervals, and then we just called this partition a generalized discrete vector field. It's acyclic because I have my function values in sequence, and so I have a gradient and I have a discrete Morse function. Does that answer your question?
So given the function, you define the vector field by saying the intervals are any simplex and its bases, they have the same radius.
All the simplices that have the same radius, if I assume general position, yeah. Otherwise, I have to be a little bit more careful. Yes. But I usually like to do it the other way around because gradients or discrete gradients are much more intuitive. Somehow first the function and then going back to the gradients seems a little bit roundabout. So I usually do it the other way around. Because once I have the gradient, I just assign function values. It doesn't really matter what. In this case, it's the radius function. All right. So now we remember the Delaunay triangulation. The radius function has this structure. So I can define the lower set of a critical simplex. Remember, a critical simplex is one that a single one in the interval. The lower set is when you have this directed graph that I showed at the end, all the nodes that lead up to this critical simplex.
Maybe for the ignorance, it would be helpful if you say what you're aiming at by defining all these things. Because
I was just about to get there, yeah.
it's nice to do it in the beginning.
Yeah, so I thought I did that when I said that I want to understand the Delaunay triangulation in blocks of simplices rather than single simplices. Why I would like to do that is because when I describe the shape locally, I would like to say this bunch of simplices I can throw out because there's a pocket. So I would like to define pockets and tunnels and this stuff in larger chunks. And these are meaningful chunks. I'll give you, after this slide, I have a few pictures, so maybe then you get a better intuition for that.
So critical simplex are the one with the unique function value?
Mm-hmm.
Is that correct?
Yeah. The reason they play a significant role is that when I add a critical simplex, the homotopy type changes. And what it means that the homotopy changes is that this simplex is now responsible for a topological feature of the complex, versus the anti-collapses, they don't create any features. Okay, so I have this lower set. And the wrap complex is just the union of all lower sets of critical simplex with radius at most some r. Okay. This definition might be very much encoded, but I prefer it to the very lengthy definition that we used to use when we came up with this concept, because this defines things like this. So this is a mechanical object. You see part of the Delaunay triangulation. The Delaunay triangulation would always be convex, but somehow these cavities from the outside, they can be pushed in, and they are pushed in by removing by collapsing as far as you can go. So this is the union of all lower sets of all critical simplices. What's removed from the Delaunay triangulation is the lower set of the infinite simplex, if you like. But this shape also has a natural tunnel going through. And this tunnel is also created by, so when you grow things, this tunnel would be created by adding a triangle at some point in the middle that prevents you from flying through the tunnel. And the lower set, the tunnel is more or less the lower set of this one triangle. I say more or less because it depends on the shape. It could be more complicated. It could be that the tunnel is actually destroyed in several steps by creating voids, and hierarchically all kinds of stuff could happen. But there are critical simplices in this tunnel, so that the union of the lower sets are exactly this tunnel. Once I can recognize that, I remove the whole chunk at once, and I get a reasonably clean description of it. This is another example where my point set has the shape of a monkey saddle, and the software doesn't know anything about the dimension or anything. So these points are in 3 dimensions, but it gives me back a 2-dimensional surface, because somehow the points describe this 2-dimensional surface, that the tetrahedra that you can imagine lie on top and at the bottom, they all in the lower set of the infinite simplex. I remove them, I get a nice description of the monkey saddle. So this is very much in contrast to, for example, analysis approaches to shape description of point sets, where you have to figure out locally what the dimension is, and then somehow to reconstruct this goes all automatic. And it's pretty fast, so this would be, I don't know, cannot even, not in integer seconds, but small fractions. Okay, and then to illustrate one application of this idea. So in biology, at the time I also worked with Andrew Ban and Johannes Rudolph at Duke University. And we used the idea of wrap in order to describe interface surfaces for protein complexes. So what is this? Okay, you have a protein complex, which means that I have 2 proteins that are somehow stuck together. And I would like to separate them. And the reason why I would like to separate them is I want to put a surface in between, so I can study a little bit of how exactly the structure of where the 2 proteins are complexed, how it looks. So we build this surface in between. You see the surface isolated here, and another one here. And naturally, see, do I have a picture for that? Oh yeah, so here you have the 2 proteins separated together with the surface. The surface is colored differently, so they differentiate the 2 sides. I think I don't have a separate picture for the surface, but just to tell you what this surface is. The protein complex gives you a Voronoi diagram in 3 dimensions. Dualize, you get alpha complex in 3 dimensions, but with colored points, colored with protein 1 and protein 2. So you're interested in the alpha edges that connect 2 different colors, and then the Voronoi surface that passes through them, so that separates protein 1 from protein 2. Okay, so you just take this Voronoi surface, that's well defined, but the problem with it is it's infinitely large. You would like to trim it back, and when you trim it back, you always have the question, well, how far do you trim it back? That's exactly the shape question. If you have a point set, like you want to shrink it in, you want to use the wrap algorithm to get some kind of reasonable boundary. And that's what we do. So that we have this infinite surface, and then we shrink it back using the logic of the wrap algorithm. We get this, not entirely perfect, if you like, because there's a little piece here. It has its justification in terms of the theory, but maybe in terms of biology, you don't want to have that, but not too often this happens. And then what we did with this is, when we had a surface, most of the time the surface is a topological disk. Sometimes actually it's not. Sometimes you have a genus. Like I remember once we had a protein complex that comes that's associated with snake poison. I forgot the chemical term for this. But they had a complex that the 2 proteins almost form a link. And when you almost form a link, then if you want to separate them, you get a genus, like a torus. And somehow intuitively it made sense, because I guess this means that this protein complex is very difficult to separate. If it's linked, how do you separate it? And that's why the poison works quite well. But usually you get disks. When you have a disk, you can make it flat in the plane. There's a nice algorithm, TUTS, embedding algorithm, where you take a disk and you draw it in the plane. So this is here. We created a geometric disk, and then we bicolored it, because both sides of the disk are interesting. On one side, it borders one protein, and the other the other protein. And then we color in regions of the amino acids where the neighboring amino acids. And so here we created these pictures where we have so a semi-transparent part, and so you can see which amino acid interacts with which amino acid on the other side. This is the same from the other direction, I think. Okay. Now to persistence. So persistent yep.
So these shapes you described with the critical points, everything you showed is based on this radius function?
Yes.
Taking different functions will lead to different surfaces?
Yes. I use a weighted radius function for the actual examples, because we have different atoms, different radii, but the theory, there's almost no difference, so I just don't talk about it. But so whenever you have different radii, all the formulas generalize, also the algorithms. Okay, so persistence is this idea that we should also quantify the topological features of shapes. And somehow this led to a completely different story. So this made me occupy the last 10 years and learn topology. And so this became its own field called topological data analysis. Has been used in high dimensions also, but I just talk about 3 dimensions. And I would like to emphasize some of the way persistence fits with wrap and with alpha shapes to make one theory. I start slowly. When you have a 3-dimensional shapes, there's only 3 possible non-zero Betti numbers, Betti 0, 1, and 2. And they have intuitive interpretations. Betti 1 counts the components of the shape. Betti 0 does. Betti 1 counts the tunnels or loops. And Betti 2 counts the voids or empty spaces surrounded by the shape. And there's a neat incremental algorithm which we've discovered with Delfinado a long, long time ago, even before I had any knowledge of biochemistry. Namely that you can construct compute the Betti numbers incrementally by adding one simplex at a time. And when I add one simplex at a time, the only requirement I have is that when I add a simplex, its faces have been added before. Okay. So if I add a vertex, I get a new component. If I add an edge, there's two cases. Namely, I merge two components, Betti 0 goes down, or I form a loop, Betti 1 goes up. Same as a triangle. If I add a triangle, either I interrupt a tunnel, Betti 1 goes down, or I complete a surface that surrounds a void, so Betti 2 goes up. And when I have a tetrahedron, a void disappears because all the four triangles are already there, they form a void, it's gone. Okay, so it's a very simple algorithm, and this is true in all dimensions. When you write it as an algorithm, it just looks like that. And the only complication that happens is there, I have to answer this question. Is my K-simplex part of a K-cycle? Unfortunately, in 4 and higher dimensions, the only way to answer this that we know is some algebraic computations, is metric reduction. But in 3 dimensions, this can be done elementarily. And so it gets a very fast algorithm. And the way we use it is, in the context of alpha shapes, we grow the balls continuously. So this already gives us an ordering of the simplices, how we add them. And so then we compute the Betti numbers just as we go. This has the extra benefit that I don't only get the Betti numbers of the end product, but at every stage. Also, I wanted to point out that somehow it's very suspicious that whenever I add a simplex, either a Betti number goes up or one goes down. I call the first birth and the other one death. It begs you to pair them up into birth-death pairs, and that's what persistence does. Here's an example. So this is grammacidin, a very small protein from 2 directions. Here you see some alpha complex descriptions of the same. The arrow shows where the radius increases. And this is the number of tunnels, or the log of the number of tunnels, so Betti 1. And when I computed this, I wanted to say that grammacidin has 1 tunnel, and so the computer should be able to find that. It didn't. It gave me, I don't know, how many tunnels do I have here? 34. So I have some around 30 and 40 tunnels all the time. Although from just looking at it, I know there's only one significant tunnel. And I wanted to figure out what this tunnel is and where it is. And that led to the definition of persistence. So here is another plot of the same graph. Here the graph is at the end. So this is the log of the number of tunnels. So you see all this stuff. And then now what I do is I compute for each tunnel when it's born and when it dies. Assuming for a second that I can actually do that. And when I have birth and death, then instead of just drawing this one tunnel, I draw the triangle forward. So the persistence forward is the difference between birth and death. And so you see one big triangle showing up. And this one big triangle is the one tunnel that is born early and dies late. And that's the tunnel that determines the function of this protein. Okay. So here's another intuitive picture of persistence when I grow balls. So here, you see the points are more or less in the shape of a circle. But when I draw it, there's all kinds of holes. So I have a number of circles. But if I grow more, the little ones disappear. The big ones remain. But one step further, I have another circle appearing. But it disappears right away again. And I wanted to point out this case. So when you have a point set, somehow we're often tempted to say, well, just get the correct radius so that you get the right shape. For point sets, in practice, this never happens. Not that we don't find the right radius, it actually doesn't exist. Because it's always overlaid with topological noise. It comes and goes. And so this cycle up there is a cycle that's born later and then disappears again. The only distinction between important cycles and non-important ones is the important ones remain. So with your eyes, you can pick them up easily because that's the only thing that remains if I do it fast. And that's what persistence does. So here's sort of a justification that actually I can also define what I just talked about. So these are homology groups within my filtration. Filtration is this term that I have a nested sequence of complexes, like with the alpha complexes, just in growing the radius. The cycles are in these homology groups, and they map from one shape to the next, or from one homology group to the next by inclusion. Because if I have a loop in one complex, the loop still exists in the next bigger complex. But it could be trivial now, because it could actually be that I have a loop here, but now the loop becomes trivial because I include the membrane or I triangle it. In which case, the image is the zero group in the next homology group. Okay, so these are linear maps. And within these linear maps, I can define when a cycle alpha is born, namely when it's not in the image of the previous homology group. And it dies when eventually it merges, its image merges into the image of the same previous group. Okay, so that's the definition of birth and death. And this gives you a pairing of birth and deaths. Sometimes a cycle only gets born, it never dies. For example, if the final complex has some cycles, we sometimes call it the essential homology. But then we usually add something at the end that is convex maybe, and then you always have these pairs. So this goes back to 2000 or something, and has been very fertile. One thing I wanted to show you is persistence is stable. And instead of proving anything, I want to show you in a little movie. Movie is just a sequence of pictures. What I mean by stable, I mean if you have two functions which are not very different, then the persistence pairing is not very different. What do I mean by this? The persistence pairing is what is expressed by a persistence diagram. Each point here is a birth-death pair. Okay, so this point here means, let's see, this point means that it's born at this value of radius and it dies at this value of radius. The points are above the diagonal because death is after birth, naturally. This is in fact the first homology persistence diagram, meaning each point there is a birth and death of a loop, one-dimensional loop, of this data set. So imagine here each ball has a center, and you grow the balls. I don't grow them because this would be a mess, but you can imagine, well, you have this empty area here, and this is this point, because it takes a while until this fills up, and it fills up exactly at the death value of this point. Oh, I should correct myself. This is the zero and the first Betti numbers. So the zero Betti numbers is this line of points. They're all born at zero because every point wakes up at radius zero, and then this shows you the sequence of merges until everything is connected. The other points are the loops. I don't show the voids. Okay, now I'm going to move the points a little bit, and you see how the diagram changes. So you see the points in the middle, they come together. At the same time, this point that was higher up above the diagonal, it comes down, goes towards the diagonal. Towards the diagonal means that the birth and the death values become similar. And now you notice this is actually a movie backwards. Starting out with a regular grid. A regular grid has this property that everything is symmetric, so there's very few birth and death events. Namely, this is really just one point, namely born at zero and die when the balls meet, touch. Because once two touch, all of them touch and everything is connected. And then we have another point here, that's the loops. So the loop is born when the balls touch. So the birth of this is the same as death of this. And the loop disappears when this square fills up. Okay, and then the movie forward again. And now you see how the balls separate because of this little knob in the table. At the same time, you see this point moving away from the diagonal. Okay, so this is illustrating that this is stable. Formally, we state it like this, that the bottleneck distance between the diagrams is bounded by the L infinity difference between the functions. The functions in the earlier example was the distance, the three-dimensional distance from the set of centers. So every point carries its distance from the closest point. And if I move my point a little bit, this distance function changes only a little bit. And therefore, I have the bottleneck distance, which is bottleneck distance between diagrams is I have a matching between two diagrams. It's the length of the longest edge. And I minimize the length of the longest edge in the matching. Okay, so we proved this a few years after starting with this persistence diagram. And then this is one of the most important theorems because it tells you that persistence diagrams give you a reliable measure of a shape. Okay, and then I tell you a little bit about expectations. So when I started this, actually, I didn't really know what I get into. And then I started to learn about stochastic geometry, and there's some beautiful stuff, work from the 70s in stochastic geometry. Studying mostly, so the particular work we're interested in, the number of simplices in the Delaunay triangulation. So the setting is we have a Poisson point process. So this is like a uniform distribution, but over the entire space. So what it really says is in two regions, the number of points in the two regions is independent, or any number of regions. And also the number of points in one region is proportional to the size of the region. And the proportionality factor is this rho, the density. So this is a Poisson point process. And it tells you of what the probability within a region is to have no point, or k points. One thing that I'm going to use is that with probability 1, the points are in general position, which means that the Delaunay triangulation is actually a simplicial complex, and that the interval structure that I talked about is well defined. If it's not in general position, then I have trouble with this, and then we usually work with perturbations in this case. Okay, and so this is the theorem. So X is my point set, Poisson point from a Poisson point process, positive density. I count everything within the domain omega. And I count intervals. And the lower bound is, the dimension is L, and the upper bound is dimension K. So I do a little bit more than just counting the simplices in the Delaunay triangulation. I counted the intervals in my partition that's given by the radius function. And there's two reasons for that. One is because I'm actually interested in this discrete Morse function. Another one is it turns out this is easier than counting the Delaunay simplices. Of course, this cannot make sense because it's easier in the following sense that we get results so that from these results we get improvements or new results for Delaunay simplices. And the reason for this, if you thought about stochastic geometry, then I think it makes sense. The reason for this is in probability is inherently local. So you would like to have a local event that allows you, for example, is this edge in a Delaunay triangulation? The trouble with asking whether an edge is in a Delaunay triangulation, this is not a local question. Because the empty sphere that passes through the 2 points could be anywhere. You don't know where it is. So it's a non-local. But I make it local by asking only for one sphere, namely the smallest sphere that's spanned by the 2 points, where the 2 points are south and north pole. Because in the other cases, I get the existence or non-existence of the edge from other information. And this is exactly the question of intervals. So if the smallest sphere of the 2 points is empty, then I know that this edge is a critical edge. If it's not empty, then this edge may exist in a Delaunay triangulation, but not as a critical edge. So it could, for example, be part of a triangle, forming in which case the triangle should be critical. So if I find out that the triangle is critical, and also that the center of the sphere of the triangle sees the edge from the outside, then I know I have an edge-triangle pair. And so I get the information that the edge is in the Delaunay triangulation from the criticality of the triangle. Similarly, I sometimes get an edge as a consequence of the criticality of a tetrahedron. So all I'm saying now is that counting intervals is actually local, like much preferred in probability theory. And I can get the Delaunay simplices, the count of the Delaunay simplices as a consequence.
Isn't that, so you say it's not local, but in your alpha shapes, it is local based on the radius, right? It's the same thing? The question whether an edge belongs to your alpha complex.
Yes.
Based on the radius, right? So
Yes. It's local once I have all the points. But in probability theory, to reduce it to an expectation, what you would do is you have 2 points, A and B, and now you ask, does there exist an empty sphere? So you specify a sphere, and then you ask, what's the probability that this sphere is empty? The trouble is there's zillions of spheres, infinitely many spheres to consider. If I consider only one sphere, namely the smallest one, then I can tell you exactly what the probability that it's empty, namely that there's no point of my process that's chosen within this sphere. I have my formula e to the minus something, and that's it. And so in that sense, once the point set is given, it's local. But before that, it's not local. Okay. Okay, so 16, we worked on this, and let's see what the result is. So the result is the expected number of intervals of this type, LK, lower bound, upper bound, this is a ratio of gamma functions. I'll show you in a second what this is. CLKN, that's the constants. So these constants were known up to 3 dimensions, and now we know them up to 4 dimensions. And the last thing, rho times the size of omega, that's just the number of points that I choose within my region from the small point process. And so here are the constants. In 2 dimensions, you will recognize the constants. So that there's actually nothing to prove in 2 dimensions, because in 2 dimensions, the Euler characteristic says if you have n points, you have 2n triangles, and you have 3n edges, minus constants, which are not counted here. And the only information in this matrix is that actually half of the triangles are critical and half of the triangles are not critical. So the non-critical triangles here, this is a triangle edge pair. So I also get n edges. So from the 2n critical edges, I get n non-critical edges. So in total, I get 3n edges. And I get 2n triangles because n are critical, n are non-critical. So in 3 dimensions, you get these numbers over there. They have been known by Miles already. So this is a result from the 70s. And in 4 dimensions, some of these numbers have been, no, none of these numbers have been known. Actually, also in 3 dimensions, these numbers have not been known. These are the numbers for the intervals. That's the first time we considered this. What has been known is for the Delaunay simplices. So here is the translation from the intervals to the Delaunay simplices. It's just a formula, and then you get the Delaunay simplices. And Miles had all the blue numbers, and then the red ones are new. And we also stuck at 4 dimensions. So in 5 dimensions, we were not able to give the right numbers. And I'll tell you in a second why. But we also know the distribution of if you increase the radius. So here, the horizontal axis is the radius, and the vertical axis is the number of intervals of type 1, 1, 1, 2, and 2, 2 in 2 dimensions. 3 dimensions, 4 dimensions. Simplified to the Delaunay simplices, 2 dimensions, 3 dimensions, 4 dimensions.
Your radius is compared to rho, or?
Yes. I would have to go back to the formula. Let's see, where is it? So you see this ratio of gamma functions. The radius is r. The rho is the density. Where is it? I'm colorblind, so I don't see this point sometimes. For example, now. Okay, so rho, nu n is the volume of the n-dimensional unit ball. R to the n, that's the radius. And this is the incomplete gamma function. Right, incomplete gamma function. And you divide it by the complete gamma function. And this gives you these curves. So the intervals are gamma distributed. The simplices in the Delaunay complex, they are not. They are linear combinations of gamma functions. Because, for example, a Delaunay triangle could come from a critical triangle or from a tetrahedron that's critical, and so on. So this gives you these curves. So for Delaunay, these are linear combinations of gamma functions. Okay, and I want to conclude with an elementary question about spheres and circles. Namely, to get these numbers that I showed you, you solve some integral equations, which it's a big mess, but it's technical hard, but otherwise nothing in it. But it reduces to a combinatorial question about circles and points. Namely, the question here is, suppose you pick 3 points on a circle, uniformly independent. What is the probability that the triangle spanned by the 3 points contains the center? That was a question to you. Anybody know?
So all of them has to be in a half circle in order to not contain a circle?
Right.
So half to the power of 3? No.
Half to the power 3, so that's 1/8.
But I'm brave enough to guess.
It's a good guess, it's not right.
It's at least twice that much, because the line on the left half more than the right half.
Yeah. So I think you're on the right path, but I want a number. It's a simple number. Ingrid, do you have a guess?
It's a quarter. No?
Yes. How do you know?
Based on what you said.
Okay. You're right, and I'll show you a proof. I pick 3 points, and suppose I pick the 3 points so that the center is actually contained. Now, if I reflect one of the points through the origin to the other side, oh, sorry, I was ahead of myself. If I decompose the triangle into these cones from the center, I can compute the area by just adding the areas of the cones. Now I reflect A, I think, yeah, 2 minus A. Then the cones that I get are still the same area because I move a point over, so the base of the triangle stays the same, the height of the triangle stays the same, but one triangle is now negative. And if one triangle is negative, this is an indication that the center is not in a triangle. Now, to pick A or minus A is the same probability. So I have the same chance of choosing B, C minus A as ABC. If I reflect another point, I get another minus sign. If I reflect all 3 points, I get 3 minus signs, and then I get, again, a triangle that contains the center. So now I have 8 possible triangles. Out of these 8 triangles, 2 of them contain the center, namely the first and the last. All the others do not contain the center. And since they're all equally likely, so this is a trick by Wendell from 1963. You have the probability that you contain a center is 1/4. This extends to 3 dimensions. So in 3 dimensions, you have a sphere, 4 points on the sphere. You have 16 tetrahedra through all the reflections. 2 contain the center, so the probability that the tetrahedron contains the center is 1/8. The strange thing, or at least at first I thought it's a strange thing, is in a Delaunay triangulation, the probability that a triangle contains the center of its circumcircle is not 1/4, it's 1/2. That's why half the triangles were critical and half were non-critical. The critical ones are exactly the ones that contain the center. And the reason is because you need a reparametrization when you do the integration. It's called the Blaschke-Betkanchin formula if you're interested in this. So you need answers for this elementary question and then the integral in order to get the numbers for the Delaunay triangulation. And maybe one thing I still indicate, you get the intervals from this picture. So when you have, say, 4 points in on the sphere in 3 dimensions, the center sees some faces of the tetrahedron. And these faces that it sees are in the same interval. So exactly when the tetrahedron contains the center, you have a critical simplex tetrahedron. If the center sees a single triangle, you get a 2-3 interval. When it sees an edge and 2 triangles, you see a 1-3 interval. So this way you get all the different cases. But unfortunately, in 5 dimensions up, this leads to a little bit complicated questions which you couldn't answer. And that's all I wanted to say. Thanks.